Today we will discuss about upper Riemann sum as well as lower Riemann sum. So before we are going to discuss about the upper Riemann sum, we need to know about the intervals. Like this is our okay, x-axis, y-axis. Okay, let us represent one function f on interval, let's say a to b. Okay, so this is one function represented on interval a to b. So here it is b. Okay, so this is our function f. Now we need to separate this function, like by using the partitions we need to separate, like a1 is equal to, let's say, I0, I1, I2, I3, and so on. Here it is IR. Okay, IR minus 1. Here it is some IR, and so on. In is equal to b. In is equal to b. So this is our partition of interval. By using this, we need to define upper Riemann sum as well as lower Riemann sum. So how? So the function f defined on interval AB, the function f defined on interval AB, necessary it let mr and small mr be the bounded. That means here it is one interval, here it is one interval like IR minus 1, and let's consider this is IR. Okay, so this is our interval from IR minus 1 to IR. Okay, from this to this is our interval, and we need to define one supremum and one infimum over the function f as particular to given interval. Okay, so capital MR means our supremum. So here it is, you need to going to discuss. So in between this, the uppercase upper M, that means the capital M is here, capital M, that means capital MR, and the small mr means the infimum, that means this. Okay, the lower part of the this graph, that is MR. Okay, this called is supremum of the given interval, infimum of the given interval. That means capital MR and small mr in interval IR minus 1 to IR. So sum means we need to collect all subintervals, like I0 to I1, I1 to I2, I2 to I3, and so on, IN minus 1 to this is IN. Okay, these are all our partitions. So we need to define all of this capital M. Okay, like capital in between I0 to I1, we need to show capital MR as well as small mr. So by using this, here it is capital MR is this, small mr is this. In between this interval, small mr again this one, capital MR is this one. Okay, so again this. Okay, so first we need to define all these intervals for upper Riemann sum is, that means the supremum. So here it is, the supremum is this mr. Again in between this interval is this mr. Again in between this interval, that is capital MR, and so on. So after this, we need to take sum of these particular supremums with respect to their delta. Delta means the length of the interval. Okay, so here it is, we define upper Riemann sum by like upper Riemann sum of the function over the partition P. Upper Riemann sum of function f over the partition P, that is capital M1 delta 1 plus capital M2 delta 2 and so on capital Mn delta n. Okay, what it means? That means the first interval supremum, sub-interval supremum like M1, here it is the M1, okay, here it is the M1, M2, M3, these are all our supremum. So we need to collect all the supremum from these sub-intervals to define upper Riemann sum. So here it is the sum of all supremum with delta r, that is summation r is equal to 1 to n capital Mr into delta r, right? So here it is representation of graph and here it is the definition of upper Riemann sum. Is it clear? So after this we need to define lower Riemann sum also, right? So let's define lower Riemann sum. Here it is lower Riemann sum. So same function we need to define on the interval AB. Okay. Lower Riemann sum. So same as usual the upper Riemann sum, just consider we need to collect all infimum here. Okay, except capital M1 we need to write small m1, so we will get all lower Riemann sum. Okay, so definition is here. Definition: the function f, the function f defined on closed interval AB necessarily it, okay, necessarily it let capital Mr and small mr be the bounded, that is supremum and infimum of given function of f in particular interval IR, that is in I is equal to IR minus closed interval IR minus 1 to IR. Okay, so we need to define the lower sum, like lower sum equal to lower sum of the function f over the partition P equal to, okay, small m1 delta 1. That means we need to define first interval infimum, okay, second interval infimum. That means here it is some small m1. In between this interval, again this is our small m1. In between this interval, again this is our small m3. Okay, m1, m2, here it is m2, here it is m3. In between also this is m4, small m4, and so on. Here it is our small mr. Like this we need to define all the infimum of these particular subintervals, so we will get lower Riemann sum. So lower Riemann sum of function f over the partition P is equal to m1 small m1 delta 1 plus small m2 delta 2 plus small m3 delta 3 and so on. We will get small mn delta n. Okay, so that means the summation of r is equal to 1 to n small m r delta r. This is our lower Riemann sum of given function over the interval AB, and this is our upper Riemann sum over the function f on given interval AB. Okay, so I hope you clear these definitions clearly, and thank you.